Hello and welcome to a walkthrough of Pearson EdXL International A-Level, the Unit 4 paper, which was sat last week, Tuesday the 30th of May 2023. It's an A2 paper. That means it's 90 marks and it's 1 hour and 45 minutes long. First 10 questions are MCQs. Question 1. In an electron gun, electrons are released from a heated filament. Which of the following is the name of this process? That is the simple definition of fermionic emission. 1 easy mark. Question 2. There's a PD of 6 volts across a 220 microfarad capacitor. Which of the following expressions gives the charge stored on the capacitor? The capacitance of a capacitor is the amount of charge stored per volt, Q over V. So if you multiply the capacitance by the voltage, you'll get the charge stored. 220 microfarads is actually 2.2 times 10 to the minus 4 multiplied by 6. The answer is B. Question 3. Question 3. A nucleus of potassium-38 emits a beta plus particle, which row of the table shows the proton number and the nucleon number of the nucleus that is produced. You should all know that in both beta minus and beta plus decay, all that's happening is that either a proton is turning into a neutron or a neutron is turning into a proton. The nucleon number remains unchanged, so it'll definitely be 38. In beta minus decay, a neutron turns into a proton and the proton number goes up. But in beta plus decay, it's the other way round. A proton is turning into a neutron, so the proton number goes down by 1. So the answer is 1838B. Question 4, which of the following gives the base units of impulse? Impulse is simply an amount of momentum. It has the same units as momentum. Momentum is mass times velocity, so kgms to the minus 1. So it's option A. Alternatively, you can think of impulse as being force times time. So take force, kgms to the minus 2, times s, and you get back to kgms to the minus 1. Question 5. Of all the questions on this paper, this is the one that made me hesitate. Scientists use particles with high energy to investigate the structure of nucleons. Which of the following statements is not a reason why particles with high energy are required? Well, clearly A is correct, to allow forces between particles to be overcome, and D, to provide sufficient energy for the production of new particles, is also correct. The question is whether it's B or C. Well, to ensure particles have very high momentum, that's very important, so they can smash into things and knock things. Is there a reason when we're investigating the structure of nucleons? Do we have to have those very small de Broglie wavelengths? Isn't that really for when you're, for example, diffracting electrons through structures and you want the de Broglie wavelength to match the size of the gap? I'm thinking the answer must be C, but I'm not very happy with that question because don't they have a very high momentum so that we have a small de Broglie wavelength? I think the answer is C, but I wouldn't want to stake my life on it. Question 6, which of the following is a fundamental particle? Well, it's not a neutron because that's made up of quarks. It's not a pion because that's a meson and that's made up of a quark and an antiquark, and it's not a proton. The answer, of course, is neutrino. A particle has a mass of 6.5 mega electron volts per c squared, which the following gives the mass in kilogram of the particle. We know that the mass is the energy divided by c squared. The energy of the particle is 6.5 times 1.6 times 10 to the minus 13, because it's mega electron volts, divided by c squared. The answer is B. Now, if you just do a quick bit of maths on this, you know that an electron is half a MeV. This is about 13 times the mass of an electron. And if you do type all those numbers into your calculator, you get about 13 times the mass of an electron. So it is B. Question 8. In the early 20th century, scientists carried out alpha particle scattering experiments. Which of the following is not a conclusion from the scientists' observations during these experiments? This is very much a classic question. You need to know that, yes, they found out that most of the atom is empty space. The nucleus contains most of the mass of the atom, or there's a concentration of mass. And they also found there's a concentration of charge in the atom. But they certainly didn't know anything about neutrons and protons. So the answer is C. Which of the following shows the beta minus decay of a nucleon? Well, that's me, beta minus decay, neutron turning into a proton. So that takes it down to A or B, producing a beta minus. The beta minus is taking away negative charge. So the charge is now balanced. The one thing that doesn't balance is your lepton number. The electron-lepton number of a neutron is 0, of a proton is 0. A beta minus, which is an electron, has an electron-lepton number of +1. So you need a little particle which has no charge, which has a lepton-electron number of -1, and that would be the anti-electron neutrino. So the answer is B. Question 10, bit of a trick question, I thought, because I nearly fell for this when I first saw it. Because I saw the wire there, I saw the 35 degrees, and I thought, oh, we're going to have to use a function. Now, interestingly, they're using a sine function, which makes no sense at all. It would have been a much better trick question if they had used cos 35, because then you'd be going, oh, 5.2, or the length times sine 35, also cos 35. But actually, it's all a red herring, because they normally give you the length of the wire, and you have to work out how much of the wire is perpendicular to the magnetic field. Well, they tell you the amount of wire that is perpendicular to the magnetic field is 5.2 centimeters. So the answer is either A or C. All right, the sine 35 is just there to mess around with you. All right, the answer is A or C. Now you get your left hand out. Get your left hand out. Stick your current going in the direction of the current. That's your second finger. Your first finger is going from north to south. And your thumb is pointing into the page. So the answer is A. Section B, structured questions. Question 11. In 2022, CERN announced the discovery of a new particle known as a pentaquark, which is made of 5 quarks. The table shows the charges on some quarks. The 5 quarks in the pentaquark are the charmed quark, the anti-charmed quark, the down quark, the strange quark, and the up quark. Some scientists said that the pentaquark is made up of a meson and a baryon, held together by the attraction of their equal and opposite charges. Determine the quark combination and charge of a meson and of a baryon that could make up the pentaquark. Okay, so mesons are 1 quark and 1 antiquark. Now, the only antiquark we have to play with is the anti-charm quark. And the charmed quark has a charge of +2/3. So the anti-charm quark must be -2/3. Now, the charge on a meson must be either +1, -1, or 0. I've got a -2/3 already. So if I add on a D or an S, I'm going to have an overall charge of -1. So the answer is either a D with an anti-charm or an S with an anti-charm. There are 2 possible answers there, and the charge is -1. So the charge on the meson is -1, which means the charge on the baryon must be +1. It can't contain an antiquark, and the charge must be +1. And so if you see what you've got left, obviously you've got a USC left, and that combines to make a charge of +1. It could be USD if you use the, yes, it could be USD rather than, no, UDC, sorry, it could be UDC rather than USC. Well, there you go, 5 easy marks. Oh, that was it, question 11. Question 12. Question 12, a particle with charge q and momentum rho, not p, rho, follows a circular path of radius r. The path is at right angles to a magnetic field of magnetic flux density B. Derive the following equation for the particle. This is the very, very famous one that you've probably done loads of times in school. R is rho over BQ. How do we get there? We write down the two equations. The force acting on a moving charged particle is BQV, and the force to make it go in a circle is mv squared over r. You make the two the same, you cancel down the v. R equals mv over bq, which is rho over bq. Interestingly, the q was little q in the equation, but they've given it here as big Q as the charge on the particle, so that's fine. So R is rho over bq, 2 marks. The particle is an alpha particle of 5.4 MeVs. Calculate B. Now, again, this is one they've asked you to derive an equation. You're almost certainly going to be using it in the very next part. So you're going to be using the equation they gave you, but they're going to have to rearrange it this time because you want to calculate B. So if you rearrange it, B is rho over RQ. Now, the question is, you haven't been given momentum of particle, but you should know 2 ways we can work this out. We can either work out, turn the energy of 5.4 MeVs into joules, and then work backwards to find the velocity and multiply by the mass. That's method A, which I try to avoid doing, because you shouldn't need to have to calculate velocity unless they ask for it. The quicker way of doing it is to know that momentum squared is m squared v squared. Sorry, that's a mistake there. Momentum squared is m squared v squared. And so all you have to do is work backwards. And so you know that the KE that you've been given, if you take the KE and multiply by 2m and then root it, you get rho. So what's the KE? The KE is 8.64 times 10 to the minus 13 joules. And then all we do is multiply it by the mass of an alpha particle, multiply it by 2, and then square root the whole thing, and you get 1.071 times 10 to the minus 19. That goes on the top. You would have got exactly the same number if you'd worked backwards to solve for V and then multiply by M. Anyway, when you do all that, you've got on the bottom, you've got the radius multiplied by 2 lots of an electron's charge because it's an alpha particle. And you're supposed to know that an alpha particle is 2 lots of an electron charge. And you end up with a final answer of 3.5 Tesla. Okay, question 13, Linacs. Linacs and cyclotrons both accelerate charged particles to very high speed. The diagram shows a Linac. So you've got a particle going through, and there are these things called drift tubes, and there are gaps between drift tubes. Explain the use of electric fields in a Linac. You should refer to the frequency of the AC supply, 4 marks. First thing you need to say, I think, is adjacent drift tubes are oppositely charged. So when one's positive, the other's negative. When a particle is in a gap, it should be repelled by the drift tube behind and attracted to the drift tube in front of it. The actual acceleration of the particle only takes place in the gap. And the time to go from one gap to the next gap must be the time for the polarity to change, which is T over 2 in the supply. The key point about Linacs is the frequency of the supply is constant. And because the particle is going faster, the drift tubes need to get longer so that you can have this constant time between gaps. I think that covers all 4 marks. B shows a cyclotron. Explain why a magnetic field is applied at right angles to the D's in the cyclotron. Well, you remember that the magnetic field there is to keep the charged particles in a circular motion. You cannot make particles speed up with a magnetic field. You can only make them change direction, because if you remember, the magnetic force is at right angles to the direction of travel. So you can't speed a particle up with a magnetic field. All you can do is deflect it. So the net force must be to the center. Fleming's left-hand rule says that the magnetic field must be at 90 degrees to the path of the particle and 90 degrees to the force. So that's why it either goes from the top to the bottom or from the bottom to the top, depending on the charge of the particle that you're trying to accelerate. Question 14. In the 1930s, scientists investigated collisions of alpha particles with protons to determine whether the collisions were elastic. The diagrams show an alpha particle before and after a collision with a stationary proton. The proton moves off at angle theta to the original direction of the alpha particle. So the key bits here are the proton was stationary before, and you are given the momentum of the alpha particle, so you know what the total momentum of the system is before. And that's the momentum of the alpha particle. And after the collision, you're told the alpha particle goes off at an angle of 10.2 degrees from its original direction. The proton is deflected at an angle theta, and you are given the momentum of the alpha particle afterwards. Now, one very quick way, which I haven't done, but one very quick way of calculating the momentum of the proton is to simply assume that momentum is conserved, and to simply deduct the momentum of the alpha particle before by the momentum of the alpha particle after, and that number must be that of the proton. We can do that. Let's go back and look at the question now. The question says, show that the momentum of the proton after the collision is about 5 times 10 to the minus 20 Newton seconds, and where theta is about 20 degrees. So the way that I teach this, I'm sure you probably do much the same thing, is you're going to have to resolve the momentum of the alpha particle. So 8.06 times 10 to the minus 20. Vertically, that'd be sine times sine of 10.2 degrees. And the horizontal component, we multiply that by the cos of 10.2 degrees. So you've got two different numbers. That's momentum vertically and the momentum horizontally. Now, you know the proton is being deflected downwards. And because momentum must be conserved in all dimensions, the vertical component of the proton must exactly equal the vertical component of the alpha particle afterwards, because beforehand, the vertical component was 0. So you know the proton must have a vertical component of 1.47 times 10 to the minus 20. Its horizontal component must simply be the difference between the momentum of the alpha particle before collision, take away the horizontal component of the alpha particle after. So you've now got two vectors at right angles to each other, and using Pythagoras, you can work out the hypotenuse, and that works out at 4.88 times 10 to the minus 20 Newton seconds, which is very close to the quoted number. And the last bit is to work out theta. Well, there you just do arctan of the vertical divided by the horizontal component, and I get 17 degrees. This is unusual in that the 20 degrees is actually quite a long way from 17, but there you go. 17, you could argue, is pretty close to 20. And that's 6 marks. Deduce whether the collision was elastic. I'm always intrigued by this, because if you have two particles and they're in a vacuum and they're just tiny little particles and they're interacting with each other, you have to ask yourself, what form would the energy take if it wasn't elastic after? I guess would they be talking about fields and some of the kinetic energy being converted into some type of potential energy? But it can't be converted into something like heat, because that doesn't make any sense, because there is no such thing as heat energy, is there? It's just kinetic energy. So anyway, so what do? We work out the kinetic energy before, and the way I've done that is I've just squared rho divided by 2m. Because that's what I do. So you get that number of joules, and you work out the EK of the alpha after, using the momentum squared divided by 2m, and the EK of the proton after. Add the two numbers together, and it's pretty close, 1.2 times 10 to the minus 12, and you just say, yes, it's elastic, and that's your 4 marks. There's probably other methods, but that's the one I like to stick with. You could go, the other method is always for an elastic collision, you should know that the closing speed equals the opening speed after collision. But when you've got them at an angle like that, it's going to be very difficult to calculate the opening speed. It's going to be very difficult to do that. Okay, that was question 14. Onward, question 15. The photograph shows a toy car inside a plastic ball. The car has an electric motor, follows a circular path in a vertical plane, so it's doing a loop-the-loop all the time. The car travels at a constant speed. That's a very important point. The student determined how the resultant vertical force on the car varied over a period of time. That's rather odd because you would normally expect a student to be recording perhaps the reaction force acting on the car, but here they've worked out the resultant vertical force, which is, of course, the centripetal force, the force to the center, the net force. And the graph shows the student's data. Now, here's the interesting thing, thinking about it, because it's doing a loop-the-loop, the magnitude of the centripetal force when you're at the bottom and the magnitude of the centripetal force when you're at the top must be the same, because you're doing a circle and you're at constant speed. So the centripetal force required to make you go in a circle must be constant in the up-down dimension. So that's why it's a symmetrical graph. The graph shows the student's data. A positive value represents an upwards force. Show that the angular velocity of the car's motion about the center of the ball is about 40 radians per second. Goodness, what a straightforward question for 3 marks. Omega is 2 pi times frequency. Frequency is 1 over time period. So omega is 2 pi over time period. Go and read the time period from the graph. It's about 0.16 seconds. So 2 pi divided by 0.16 is 39.3, which is very close to 40 radians per second. That is an extremely easy 3-marker. The student took measurements of the ball and wrote down a value of 86 millimeters. Deduce whether 86 millimeters was the radius or the diameter of the ball. Mass of car, 9.5 grams. Now, you know the maximum force up or down, which is 0.63 newtons, represents the centripetal force. And the formula for centripetal force is m omega squared r. You've got omega at 40, or you can use your more accurate figure of 39.3. Rearrange it. Radius equals 0.63 from the graph, divided by 9.5 times 10 to the minus 3 kilograms. I never try converting in my head. I always turn grams into kilograms just by multiplying by 10 to the minus 3. It's much safer. Multiplied by omega squared, and you get an answer of 43 millimeters. So the 86 millimeters must be the diameter. Very straightforward 4 marks. Here's a 6-marker with a star on it. Goodness. The magnitude of the force exerted by the ball on the car was greatest at 0.04 seconds and least, i.e. most negative, at 0.12 seconds. Now that's interesting. The magnitude was least at 0.12 seconds. 0.12. I'm just thinking about this. I'm not sure the wording is quite correct because I thought that magnitude didn't take notice of direction. The magnitude is greatest at those 2 times. It says it's least. The magnitude is least. No, the value of the force is least. I think the question's that. I think that's the wrong use of words because the magnitude is minus 0.63, but it's the same magnitude as the other one. It's got the opposite sign on, isn't it? I thought magnitude was the value with the sign stripped off. That's interesting. Anyway, Discuss the position of the car at these two times. You should consider the forces acting on the car. You do not need to do any further calculations. Right, so what's happening? At 0.04 seconds, the upward net force is greatest. And you need to say, I haven't written this, but you need to say, this is the point at which the car is at the bottom. And it is accelerating upwards towards the centre. And you can draw yourself a little free body diagram. It's got weight going down, which you can put the numbers on if you want, but I don't think you're going to need marks for that. It's got a big reaction force going up, and the net force is 0.63. You can actually calculate the reaction force there if you want to at 0.7232. And here's the bottom idea, is that the net force is reaction force minus weight. That's bound to get you a mark. All right, so the net force up is reaction force, take away the weight of the car. And at 0.12 seconds, you are right at the top of the loop. There are two forces acting on the car at that point. There is the weight of the car and there is reaction force. And the two together are producing the net force to make you go in a circle. Again, if you do the maths, you end up with the reaction force being 0.5368 newtons. And you can then say that the net force acting is the reaction force plus weight at the top. And you could then go on and say the difference in the reaction force between the top and the bottom is twice the weight. That's something you should all know about loop-the-loops. I think if you write all that down and you write some nice sentences, you should get all 6 marks there. Okay. Question 16. A search coil is used to investigate magnetic fields. The search coil consists of a coil of thin copper wire connected to 2 output terminals. A student placed the coil in a magnetic field with the axis parallel to the direction of the field. If you put a coil in a magnetic field like that, you are maximizing flux linkage with the coil. The coil was rotated through 90 degrees, so the axis was perpendicular to the direction of the field as shown. In that position, the flux linkage will be 0 at that position. As the coil was rotated, a potential difference was detected across the terminals. Explain why a potential difference was produced as the coil was rotated. So what's happening here is that potential difference is equal to the rate of change of flux linkage. In fact, technically, it's the rate of change of the flux, or the magnetic flux multiplied by the number of turns in the coil. But all you need to say is the rate of change of flux linkage. And because the amount of flux linkage is changing from a maximum to 0 over a period of time, there must be an EMF produced. B shows that the initial value of magnetic flux in the coil is that number. Now, magnetic flux is simply equal to B times A. We are not including the number of turns on the coil. That would be magnetic flux linkage. That would be BAN. So we're talking about magnetic flux. So it's B, which is 0.18, multiplied by the area of the coil. And the area of the coil would be, the radius would be 12.5 millimeters. So 12.5 squared, 12.5 millimeters squared times pi, times that number. I get 8.8 times 10 to the minus 5 Webers, which is very close to the figure of 9 times 10 to the minus 5. So we're showing it. And then we go on to part C. The graph shows the magnetic flux in the coil while the coil was being rotated. And interestingly, notice that at time 0, the magnetic flux there is this 8.8 figure that we calculated earlier. And as it rotates, it's going to go from a maximum value to a 0 value, which is exactly what happens. And it says here, determine the maximum PD produced across the terminals. The maximum PD. Usually they ask you for average PD, but here they want maximum PD. And you should be aware that the maximum PD will be produced when the rate of change of flux linkage is at a maximum. So when the line is steepest, And the line is steepest at 0.3 seconds at the bottom there. Now, you can either just look at the line down at the bottom, or you can try to draw a tangent to get the gradient of the graph. I've drawn a quick tangent here. You can see that the slope, it's quite difficult to be exact about this, is going to be about 10 times 10 to the minus 5 divided by 0.2. So, in fact, the original number I wrote down here, I was just looking at this very bottom bit, and I was saying a change of 1 times 10 to the minus 5 divided by 0.02. And since then, I drew the line, but it's the same number. All right, so the rate of change of flux, the rate of change of magnetic flux is 5 times 10 to the minus 4, but the linkage is that number times the number of turns on the coil. So you multiply it up by 5,000 and you get 2.5 volts. 2.5 volts for 4 marks. Easy peasy. Part D. The output terminals of the coil are connected together while the coil is in the magnetic field. The diagram shows a cross-section through one turn of the coil. X is on one side of the coil. The reason they're connecting it together is to make it into a circuit, so that if there is an EMF, the EMF then can then produce an induced current, and a current can flow. The coil is rotated clockwise in the magnetic field, causing a current in the coil. The student states that the current at X is into the page. Deduce whether the student's statement is correct. You should refer to Lenz's law. I'm not sure where you're going to get 4 marks out of this. 4 seems rather generous. Do you agree that if I try to push X to the right, because I'm moving a conductor in a magnetic field, nature, at right angles to a magnetic field, nature doesn't want me to do that. So the force acting on the wire will be to oppose the motion. So the force acting on the wire will be to the left at X. And so that nature will produce a current in the wire at X to produce a motor effect and a force pushing it left. So get your left hand out, put your first finger down the page, have your force arrow to the left, and you'll notice that your current is going into the page. That's one way of showing it. The other way of showing it is simply saying, well, I've got a moving conductor, and use Fleming's right-hand rule to determine the direction of the induced current. So if you now use Fleming's right-hand rule, again going down the page, the movement this time is to the right, the movement of the wire. The current induced again is into the page. So whether you use Fleming's left or Fleming's right, you're going to get the same answer. I hope that's straightforward. Question 17. A potential difference of 5,000 volts is applied across 2 vertical metal plates. A sphere with a conducting surface is suspended by an insulating thread and touches the positively charged plate as shown, and the sphere becomes positively charged. And then it says the first part is A, complete the diagram to show the electric field around a positively charged sphere. Now, I have to be honest here, I'm not sure whether they mean by show the electric field, whether you just show the electric field lines, or you show the electric field lines and the corresponding lines of equal electric potential, the equipotentials. I don't know the answer to that question. I do know that if you just copy out of the book what they have in the book for a positive charge, you must get full marks. So in terms of the electric field lines, we know that electric field lines show the direction in which a small positive charge would move at that point. And so if it's next to a positive charge, it's going to move away. So you're going to draw radial force lines or electric field lines moving away from the center. And you know that as further away you are, the weaker the electric field strength, and therefore the further away are the equipotentials. So I would draw some equipotentials, and the idea is they're concentric, and as they're further away, the gap between them gets bigger. So what I've drawn there should certainly get you 3 marks. Whether you have to label the equipotentials, I don't know. But anyway, I'm pretty sure that will get you 3. BI shows that the charge on the sphere is about 10 nanocoulombs. Potential at surface of sphere is 5,000 volts. Radius of sphere is 20 millimeters. Okay, so we look in the back, we get the formula out. Electric potential is KQ over R, rearrange. Q is electric potential times R over K. So it's 5,000 times 20 millimeters divided by K, and that's 11.1 nanocoulombs, so pretty close to 10 nanocoulombs. That was a very straightforward question. II, the sphere moves away from the positive plate and comes to rest at an angle theta to the vertical. Show that the horizontal force on the sphere is about 5 times 10 to the minus 4 newtons. Distance between plates equals that. Now, don't overthink this. This is a straightforward question. You don't have to draw diagrams with the involving tension and weight. We're not doing any of that. All we're doing is we're thinking about the horizontal force acting. The horizontal force acting on it is the electric static force of the electric field between the plates acting on the charged particle. So we know that electrostatic force is electric field strength times charged. F equals EQ. So E must equal, we're working out E first, so E is 5,000 volts divided by the distance, because the formula for electric field strength is volts per meter, so voltage divided by separation distance in meters. And that gives you 4.76 times 10 to the 4 newtons per coulomb. When I first ran through this, I jumped and thought, oh, that's the same answer. It isn't, because my answer is 10 to the 4, not 10 to the minus 4. I then forgot to multiply it by the charge that we previously worked out. You now multiply the electric field strength by 11.1 nanocoulombs, and you get about 5.3 times 10 to the minus 4 newtons, which is close to the number given. There we go. Straightforward 3 marks. I show that theta is about 1 degree. So again, you don't need to overthink this. You don't need to draw the tension and think about angles. It's very straightforward. What you've got to do is you've got to draw a little free body diagram, have the weight going down, calculate the weight. I'm turning it into millinewtons to make it easier. The weight is 26.5 millinewtons, and the force acting sideways, which we just worked out, is 0.53 millinewtons. And then all you need to do is arctan it. And if you arctan 0.53 over 26.5, you get about 1.1 degrees. That's it. C. A second identical charged sphere is held in a fixed position. The first sphere, attached to the insulating thread, is placed near to the fixed sphere. The spheres exert a repulsive force on each other. The force between the spheres is that number. Calculate the distance between the centers of the spheres. Charge on each sphere 12 nanocoulombs. 3 marks for the most straightforward calculation. You are told the force between the spheres. And we know from the appendix, we know that that is K, Q1, Q2 over R squared, separation squared. So R squared will equal K times 12 nanocoulombs times 12 nanocoulombs divided by the force. And when you do all of that, the distance between the centers of the spheres works out at 2.6 millimeters. That's question 17. We're now on the very last question, question 18. A student planned to use a capacitor in a timing circuit. The capacitor was connected in series with a resistor to determine the capacitance of the capacitor. The capacitor was charged while measuring the current I in the circuit, and the following graph was plotted. Now, this is charging Okay, so what's going to happen is you're going to start with a high current, and it's going to drop down to a very, very low current. The value marked on the capacitor is 22 microfarads. Show that this value is correct. Resistance of resistor is 240 kiloohms. So the way that you go into this is you need to realize that because they've LN'd the current, the time for the current to drop by a factor of e to the minus 1, or alternatively, the time for the current to drop by a factor of 1 on this graph is RC. So the gradient of this graph is 1 over RC. So if you work out the gradient of the graph, it's about 11.5 times take away 9.6 divided by 10 seconds. It's about 0.19. And the reciprocal of that is 5.26 seconds. And then we compare that to the RC value that we've from the values. So 22 times 10 to the minus 6 times 240 times 10 to the 3, 5.28 seconds. So we're comparing 5.26 seconds from the graph to 5.28 seconds. That's certainly close enough. So the values are correct. Straightforward. B. The capacitor was used in a circuit to time a collision between two identical metal spheres. The spheres were suspended from wires. The wires were connected to the circuit as shown. When the wires hang vertically, the spheres are in contact with the discharging circuit, and the discharging circuit is complete. So whilst they're in contact, discharging is going on. Switch X was closed to charge the capacitor. The switch was then opened and sphere A was released. Sphere A collided with sphere B. When the spheres were in contact, the capacitor partially discharged. Sphere B moved to the right. The maximum height h of sphere B above its starting position was measured. Calculate the maximum speed of sphere B after the collision. Okay, this has got nothing to do with capacitors, RC time, or anything else. This is a straightforward question of working out the kinetic energy that was given to be at the bottom must equal the change in GPE as it went up by 1.1 centimeters. So V squared is 2G delta H, and you can solve, and V is 0.46 meters per second. That's it. This is one of those questions where you're going back over topic 1 material. It's nothing to do with capacitors or anything else. It's a straightforward K equals GPE question. All right, so you got your maximum speed, 0.46. II, calculate the time for which the spheres were in contact. And you're given all that information. Now, this should be bread and butter stuff to you. You should know that the relationship between the two voltages, Ln, gives you minus T over RC. So you Ln 5.43 divided by 618, and you get minus 0.1294. And you know that equals minus time over RC. You know RC because they're telling you it's 49 times 22 times 10 to the minus 6. So if you multiply the RC by the number you came up with, you get the time. So the time is 1.39 times 10 to the minus 4 seconds. Probably quite a lot of work for 2 marks. Probably worth 3, but there you go. 1.39 times 10 to the minus 4. And that brings us to the very last question. Now, can I remind you, it says II, which means it's a linked question. The chances are that you're going to be using the time you calculated here to answer the very last question. The student stated that the average force acting on sphere B cannot be more than the weight of sphere A. Deduce whether this statement is correct. You're given the mass of each sphere. Well, there's loads of ways you can do this. The first way I looked at this is I said, well, look, let's calculate the weight of the sphere first. So the weight of the sphere is 0.275 newtons. And if that was the average force acting, the momentum transferred would be 0.275 times the tiny time, and you'd end up with 3.82 times 10 to the minus 5 newton seconds of impulse transferred. Now we know that impulse is mv. So if we divide by the mass, we'd end up with a velocity of a tiny number, far too slow. So this doesn't look right. Doesn't look like it can be that force. So the other way we could do this is to go back and then say, oh, well, what's the momentum of B at the start? We know the speed and we know the mass. So we know the impulse. 0.012, or call it 0.013. So that must equal mv. Or sorry, that must equal force times time. So if you now divide that by the tiny time, you get a massive force of 93 newtons. So the student is clearly wrong. All right, the student is wrong. Okay, the average force has got to be massive because you've got such a tiny time of contact. That's the end of the final question. Wasn't really a Unit 4 question, was really a Unit 1 question, but there you go. I hope you found this walkthrough useful. Look forward to posting some more. Thank you.